Basically, our discussion was on fixed points and stability of fixed points. So we had plotted x dot versus x, and we confined our analysis to sinusoidal function. And we saw that some points are stable fixed points and some other points are unstable fixed points. The stable fixed points were attractors and the unstable fixed points were repellers. Then we also discussed about the sensitivity to initial conditions. The response of the system is sensitive to initial conditions. So for different initial conditions, we get different trajectories with respect to time. Basically, the time series would be different. The nature of response would be different. Now let's make it more generic by keeping away the sinusoidal function and making it a generic function f of x. So let me draw the figure again. This is x dot versus x again. So this is x dot and this is x. Now I'm taking a generic function where it looks like this. So here again we repeat our analysis. In this region, in the leftmost region, what happens is your x dot is in this region, your x dot is greater than 0. So the arrow here is towards right. Then in this region, you have x dot less than 0. So your arrow is towards left. Then here again, the arrow is towards right as the x dot is greater than 0. So now we again get two different fixed points. One is this one, and another one is, I'm changing the color here, this one. So here also, which one is stable and which one is unstable?
Negative side one is stable and positive side one is unstable.
Yeah, so this is basically an attractor, right? This is an attractor. This is a repeller. So this is unstable. This is stable fixed point. Now, as before, we imagine that a fluid is flowing along the real line. This is the real line, right? This is the real line. The fluid is flowing along the real line with a local velocity f of x. Here the velocity is f of x, which is x dot. Okay, which is x dot. Then we term the imaginary fluid as phase fluid and the real line through which the fluid flows as the phase space. So we introduce two terms here, phase space and the imaginary fluid which is flowing along the real line with a local velocity. The fluid is called as the phase fluid. Okay. Now the flow is to the right where f of x is greater than 0. F of x is x dot. Okay, and the flow is to the left where f of x is less than 0. Now to find the solution to x dot equals f of x, starting from some initial condition, we are going to vary the initial condition x naught. X naught is x of t when t equals 0 is x naught. Okay, so from any arbitrary initial condition x naught, we place the imaginary particle on the phase space, which is termed, which is already termed. So the phase point moves, and we'll watch how it is carried along by the flow through the real axis. And as time goes on, because this is a function of time, x of t, so as time goes on, the phase point moves along the x-axis according to some function x of t, and the function is called the trajectory. So x of t is called the trajectory. Okay, but we know that at x dot of t equals 0, we have some x which is x star, which is the fixed point, That means that the dynamics is stopped now. Dynamics with respect to time is not there. The response is already trapped in a particular operating point, which is static, which is a static point or a fixed point or an equilibrium point. From there, if the system is again disturbed in some direction, then only it will have a response. But the nature of response depends on the initial value or the initial condition. So the function is called the trajectory based on okay. Now the x of t, the trajectory x of t depends on x naught, right? If you take x naught, you will get a different trajectory. Then if you take x naught dash, you will get a different trajectory. So basically the response itself is sensitive to initial conditions. Now to get the solution of the differential equation, x dot equals f of x. That is our differential equation, first order differential equation. If we solve that, we'll get the trajectory of the solution, or the trajectory based on some x naught, some initial condition x naught. Now we term this plot x dot versus x as a phase portrait. This plot of x dot versus x, we term it as a phase portrait. Now the appearance of the phase portrait is controlled by the fixed points x star. The fixed points x star. The appearance of the phase portrait. It is evident from this figure which is drawn here. Now for f of x star equals 0, we know that it corresponds to some stagnation points or static points of the flow. And we have already obtained two different points where one is stable and another one is unstable. The flow is away from the unstable fixed point and the flow is towards the stable fixed points. Now let's see an example. In the example, let's before going into the definition of 1 minute. Okay, before going to the definition of bifurcation, we'll just see an example. So I'm taking here an example, x dot equals x squared minus 1. Okay, now you are asked to classify the stability of different fixed points for this function or for this differential equation. So this is f of x. F of x equals x dot equals x squared minus 1. Now to find the fixed point, what should be the condition? What should be the condition for finding the fixed point? X dot equals 0, right? X dot equals 0, for which if we find x, you will get x star, which is the fixed point. So f of x star equals 0. And we solve for x star. Okay. So what's the solution here for f of x star equals 0? X star can be, what is the solution
plus
for this expression? Plus or minus
1.
Okay. Now to determine the stability, we plot x dot versus x. So x squared minus 1 is x dot, right? X squared minus 1 versus x. We are plotting x squared minus 1 versus x. Now let's see the, okay, 1 minute. Let me, okay, here I'll draw. So this is x dot, this is x. Now okay, now I am taking the, so this is my f of x equals x squared minus 1. Now again, I am getting here a stable fixed point, and here I am getting an unstable fixed point, right? An unstable fixed point. So the flow is to the right, where x squared minus 1 greater than 0. X squared minus 1 is x dot. So flow is to the right here, which is x squared minus 1 greater than 0. And to the left here, in this point, to the left where x squared minus 1 is less than 0. Now, x star is the equilibrium point. X star equals minus 1 is this point, right? This point. This is a stable or unstable fixed point. This is a stable fixed point, and this one is x star equals plus 1, which is an unstable fixed point. Now note that the definition of stable equilibrium is based on small disturbances, because certain large disturbances may fail to settle down. Because if you disturb the system, it can have some oscillations and finally it will settle down at t tends to infinity. At t tends to infinity, when it settles down, further x dot is not there, or change with respect to time is not there. So it is trapped inside a fixed point, and whether that fixed point is stable or not, to analyze whether that fixed point is stable or not, we have to give a small disturbance again and check whether it comes back to the same fixed point or it goes away from that fixed point. So if it goes away from the fixed point, it's like x star equals plus 1, because when I am disturbing the system from this point, it goes away from the fixed point, but when I am disturbing the system from this point, it comes back to the original operating point. Now, to emphasize the aspect of stability, we sometimes term x star equals minus 1 as locally stable point. Locally stable point. Why we are terming it as locally stable point? Because we confine our analysis to small disturbances. Because from x star equals minus 1, if we give a very large disturbance, it may go to another operating point. So this is valid only if the disturbances are small. To show that, we call it as a locally stable point. Okay, now I'm going to apply this on a real circuit. We are slowly going to an electrical application where an RC circuit will be analyzed. So I'm taking here an RC circuit. R is there, C is here. Now we have a switch here. This is the voltage. So this point is grounded. Now we have a current I. This is V0. Okay. Now, considering this electrical circuit, the RC circuit, in which the resistance is connected in series with a capacitor and a battery of constant DC voltage V0. And we analyze the circuit for closing of the switch at t equals 0. Closing of the switch at t equals 0. And there is no charge on the capacitor initially. We assume that there is no charge on the capacitor initially. That means Q of T0 is, which implies Q at t equals T0, where T0 equals 0. Okay, this is equal to 0. Okay, initially the charge is 0. Now you are asked to sketch the graph of Q of t, because here the characteristic variable we are going to consider is the charge in the capacitor with respect to time. So with respect to time, if you are able to draw the Q of t, then that is the time series of Q of t, or the trajectory of Q of t. Okay. Now we'll first write the equations. So minus V0 plus, how will we write it? Ri plus Q by C equals 0. Right, where I is the current flowing through the resistor, and this current is what causes the charge to accumulate on the capacitor at a rate q dot equals I. So this is basically dynamics of charge q dot, because q is a function of time and q dot equals the current I. Okay, that is the cause of current flow. Now, if you substitute this q dot equals I in this equation, because our characteristic variable is q, and what we are trying to analyze is the sketch of trajectory of q. So we want to represent everything in terms of q. So this can be represented as, this equation can be rewritten as q dot equals f of q equals v naught by r. I'm dividing throughout by r, v naught by r minus q by rc. How we are getting this? For I am writing q dot, right? Because q dot is I. This q dot is I. Okay. So for I am writing q dot, and q by c is already there. Q by c is already there. So now the equation has completely converted in terms of q. Converted to an equation in terms of q. Okay, so from this I am writing q dot equals f of q equals v naught by r minus q by rc. So this is my equation. Now I want to sketch the trajectory. Okay, so here I am going to sketch the trajectory. This is q dot, this is q. Now I am sketching it like this. This is the sketch. So the graph of f of q is a straight line, because how does this equation look like? This look like mx plus c, right? So I'm drawing a straight line here, but your m is minus 1 by rc, minus 1 by rc. So this is negative, your slope is negative. So we have a line here having its slope as negative. Okay, so this is what is your phase portrait. We termed it as phase portrait, q dot versus q. These are the two variables for which we are drawing the plot. Now, where is the fixed point here? Where is the fixed point? Anybody?
CV not, sir.
So q dot equals 0 is the fixed point, right?
Yes, yes.
Where is that point? Here.
CV.
Right, q dot equals 0. So this is q star. This is one equilibrium point, one fixed point, right? And we have to see whether this fixed point is stable or not. Now, here you have q dot as positive in this region, so the arrow is to the right side. Here you have q dot as negative, so the arrow is towards the left. So now this is a stable fixed point, right? This is a stable fixed point, and this happens, I mean, Adarsh only told now, this happens at q star equals CV naught, right? Q star equals CV naught. F of q equals 0. F of q equals 0 happens when q star equals CV naught. So the flow is always towards q star here, the fixed point q star, which is a stable fixed point. In fact, it is globally stable in the sense that it is approached from all initial conditions. From any initial condition, if you start, finally what is going to happen is q star, it will settle down at q star equals q dot equals 0. Q star where q dot equals 0, or q star equals CV naught. Now we are going to sketch q of t. So how to draw q of t? We initially q of t we'll draw for let us see the, I mean, I'll do one thing. I'll take another this thing. So here CV, this is t. To sketch q of t, I have q here and t here, and this is your CV naught. CV naught. So I'm going to draw this one. Okay, so what happens here? Initially Q dot decreases, no, not initially, Q dot decreases linearly, right? Linearly, which we have already seen from this one. Q dot decreases linearly. That means the change in charge in the capacitor with respect to time decreases linearly. So when it reaches the, but you can see here until this point, when it increases like this, Q dot is decreasing, right? When you are going through the real line, the Q dot is decreasing. And after this point, what happens? After this point, what happens? What happens to Q dot? Q dot is still decreasing, but the direction is reversed. The direction is reversed. Now Q dot, so this is what happens. Q dot decreases linearly as it approaches fixed point. Q dot decreases linearly when it approaches fixed point. Fixed point. Therefore, Q of t is increasing. Q of t is increasing and it is concave down. So here Q of t is increasing and it is concave down. Now there is one more problem which you can see from the textbooks, textbook written by Strogatz. You can do this example: x dot equals x minus cos x. Do it as homework. X dot equals x minus cos x. Now I am directly going to the bifurcations. We have three types of bifurcations to, in this course to study: saddle node bifurcation, then pitchfork bifurcation, and transcritical bifurcation. I'll first go through the saddle node bifurcation, and maybe I can show you an example also, a real world example after the discussion on saddle node bifurcation. So let's take that. Yes. So I'm going to the next page now. Again, I'll take the page with ruler. Okay. So we have already seen that the dynamics of vector fields on the line is limited, and all the solutions either settle down to equilibrium or they go to infinity, or either they'll go away from the fixed point or they can be attracted to the fixed point. Now we have an interesting thing to be noticed with these one-dimensional systems. These one-dimensional systems response is dependent on the parameter variations. We'll see what is parameter variations. That is a qualitative structure of the flow which we have seen through the real line. In general, we call it as the flow. So the qualitative structure of the flow can change as the parameters are varied. In particular, that is the nature of fixed point, whether the fixed point is created or destroyed, their stability can change, and these qualitative changes in the dynamics are called the bifurcations. That means the qualitative pattern of the response of the system with respect to variations in parameters. So this the drastic qualitative change that happens with respect to dynamics of the system and with respect to the variations in parameters is known as the bifurcations. We'll see what is bifurcations in detail. This is just a definition, bifurcations. Now let's see an example. We have, the bifurcations are very significant with respect to nonlinear control parameters because it provides models of transitions and instabilities for some control parameter when it is varied. Okay, so we'll see one system here. We have a weight here and a beam. This is a beam. This is a weight and it's fixed here. Okay, now this if a small weight, if this weight is small, I'll take another color. If this weight is small, what happens is the beam will be sturdy, right? It will not bend. The beam will be sturdy. Now, if you are going to increase the weight, I'm going to increase the weight. So the beam may not be able to support the load and it may not remain vertical like this. What happens is it bends. Sometimes it may bend. So it will look like this, right? It will look like this when the load is too heavy. So the vertical position becomes unstable and the beam may buckle. So here the weight plays the role of the control parameter. Here I'm assuming that the weight is the control parameter. So what was the definition of bifurcation? The qualitative structure of the flow can change as parameters are varied. So here the control parameter is weight. So when I'm varying the weight, the qualitative structure is varying, right? So the deflection of the beam from the vertical plays the role of the dynamic variable x. If I'm taking the dynamic variable x as the deflection of the beam from the vertical position. This is the vertical position, right? Deflection of the beam from the vertical position. So load is the control parameter. When it is increased, it deflects, right? And it buckles. So that is what happens. In general, this is one example of bifurcation. Now we'll move on to specific bifurcations. The first one is saddle node bifurcation. So let's go to saddle node bifurcation. Let's see what is saddle node bifurcation. We'll take an example. The saddle node bifurcation is the basic mechanism by which the fixed points are created or destroyed. You just keep this definition in mind and we'll go to the analysis. Once again, I'll repeat, the saddle node bifurcation is the basic mechanism by which the fixed points are created or destroyed. We have already seen the fixed point. You visualize that we had stable and unstable fixed points. So they say that either fixed points are created or destroyed in saddle node bifurcations when a parameter is varied. So as a parameter is varied, we'll see how the fixed points are created or destroyed using an example. So I'm taking an example here, x dot equals r plus x squared. This is a typical example we analyze for studying saddle node bifurcation. Now r is a parameter here. R is the parameter, which is a control parameter. So we vary r and we see the dynamics of the system, qualitative change in dynamics of the system. This is a prototypical example for analyzing saddle node bifurcation. Now, this r can be positive or negative or zero, right? R can be positive or negative or zero. These are different. I mean, there can be different ranges of r. The range of r can be in the negative side, it can be in the positive side, or r can be zero. So when r is negative, what happens? We'll see through the plot. Okay, so I'm taking here again x dot versus x. Okay, so here this is what I'm getting. Now here I have this as a fixed point which is stable, right? Which is stable, and this is another fixed point which is unstable. So this is stable, this is unstable. Now we'll see what happens to these fixed points when the control parameter is varied. What is our control parameter here? R is the control parameter here. So for r less than 0, this is our figure. Okay. Now slowly I'm taking this r to 0. So I'm going to vary r and I'm making it 0. So what happens is this parabola, this moves up, right? This moves up and this point moves up when R is moved from negative to positive side, and when R reaches 0, this point is at origin. So how will it look like? It will look like this. Here, this is a point. Okay, it's not properly drawn, but this is a point. So now here x dot versus x, it moved up. Now, what happened when it moved up? As R approaches 0 from below, it was below here. When R approaches 0 from below, the parabola moves up and two fixed points move toward each other. Right? These are two fixed points. These are two fixed points. They move towards each other and collapse at this point. Right? Collapse at this point. The fixed point collapse into a half stable fixed point. This is known as a half stable fixed point. We'll see what is that. Half stable fixed point where x star equals 0, because at this point we have x dot equals 0, which is equal to x star, right? This happens at x star. This type of fixed point is extremely delicate because it vanishes as soon as r greater than 0, right? Because from this point again, if we vary the parameter r to the positive side, what happens is the fixed point is gone. No fixed point at all. It moves up. The parabola moves up. Then we don't have a point defined for x dot equals 0. So there is no fixed point. But if we move r towards negative side, what happens is immediately two fixed points are generated. These are the two fixed points. Two fixed points are generated. So when r is varied from negative to positive side, and when r reaches 0, what happens is two different fixed points collide and a single fixed point is generated. And further, if r is varied again to the positive side, then that fixed point is also destroyed. So here what happens is, initially itself in the saddle node bifurcation, we defined that it's a basic mechanism by which fixed points are created or destroyed. So what is happening when we vary the control parameter r from negative to positive side? The fixed point is destroyed. Now, instead, if we are varying the control parameter r from positive to negative side, what will happen? The fixed points are generated or created, right? Because here, this is the case for r greater than 0, right? There is no fixed point at all. Now, if I'm varying r towards negative side, and when it reaches 0, one fixed point will be there. Then further, if I vary the r value to the positive to the negative side, then two fixed points will be there. So here fixed points are created, and in the other direction the fixed points are destroyed. So this is what happens in a saddle node bifurcation. So we say that a bifurcation occurred at r equals 0. A bifurcation occurred at r equals 0. Since the vector fields for r less than 0 and r greater than 0 are qualitatively completely different. They are completely different, right? So the bifurcation point is r equals 0. That is why we call it as this point as extremely delicate point, because in two different directions of variations of control parameter, the qualitative structure of the dynamics completely changes. I mean, they're totally different in the two different directions. Now, I will stop here. Let me stop the recording.